You and I live in a strange kind of comfort. We look at crisp telescope images on our screens, and it feels like the universe is already mapped out and labelled. The Milky Way has been photographed. Distant galaxies have been catalogued. Black holes have been simulated. It is easy to believe that astronomers have already scanned almost everything, and that space is now a story of tidying up details. Yet the real numbers tell a very different story. By the end of this video, that comfortable picture will be gone. And if you want to keep exploring the unknown parts of the cosmos together, remember to like this video and subscribe so you can join us on the next journey. Start with the sky you can see with your own eyes. On a dark night far from city lights, the human eye can pick out perhaps a few thousand stars at once, across the whole sky, including the part that is below the horizon right now. That adds up to roughly 9,000 individual stars that a person could see over the course of a year. 9,000 sounds like a lot until you remember what those stars sit inside. Our galaxy, the Milky Way, contains something like a few 100 billion stars. The stars we can see with the naked eye are not a representative sample of the galaxy. They are a bright, nearby skin over a vast hidden population. Now extend this idea one step outward. The Milky Way is only one galaxy among many. The part of the universe that we can in principle observe contains on the order of 2 trillion galaxies. That number is so large that it hardly feels real. If you tried to count one galaxy per second, it would take you far longer than the age of human civilization to finish. Yet our actual detailed observations reach only a tiny sliver of that enormous set. We have taken a handful of careful samples from an ocean and then drawn an atlas of the world. So what does it really mean to say that we have observed a galaxy? There are levels to that word observed. At the most basic level, a galaxy might be detected as a faint smudge on a survey image. It contributes a few pixels that stand out just enough above the background noise for software, or a human eye, to say there is something there. At the next level, its position and brightness are catalogued, and it becomes an entry in a database. Only at a much higher level do we have a spectrum for that galaxy, a breakdown of its light into colours that reveals its distance, velocity, and chemical makeup. When astronomers add up how many galaxies we have detected in some way, they reach numbers on the order of hundreds of millions. That sounds impressive until you compare it with 2 trillion. The best estimates suggest that the galaxies we have studied in real detail amount to around 0.0025% of all the galaxies inside the observable universe. Imagine drawing conclusions about an entire forest after examining only a few leaves. That is close to what we are doing with the cosmos right now. The illusion comes from how our brains handle large numbers. Once a number gets big enough, anything even remotely close feels like all. Modern imagery multiplies that illusion. When you see a deep field photograph filled with thousands of galaxies, it feels like a direct portrait of the universe. The mind quietly assumes that if every patch of sky looks like this, then we basically know what is out there. Yet those images come from very small regions and very long exposures. They are more like drilling a thin, deep well through the sky than taking a wide panorama. In most directions, we have never stared that long or that carefully. The map on your screen hides the empty places where we have barely looked. Even the phrase observable universe quietly misleads us. It does not mean a region we have actually examined in detail. It means the region from which light has had time to reach us since the Big Bang, given the age and expansion of the universe. In principle, we could map every galaxy in that volume. In practice, we are nowhere close. The part of the universe that has been deeply surveyed so far is more like a scatter of small patches and pencil-thin beams. Our cosmic database is full of holes, and yet we often speak as if the picture were nearly complete. There is a deeper psychological trap woven into all this. When you learn that there are hundreds of billions of stars in the Milky Way, and trillions of galaxies beyond, it can be overwhelming. The mind responds by compressing the whole thing into a single fuzzy idea. The universe becomes a kind of mental wallpaper, a background that feels complete simply because it is too vast to imagine missing pieces. In that blur, it is easy to forget that every single data point we have comes from a telescope pointed at a specific place for a specific amount of time. Anything outside those choices is still an unknown. As we move through this story, we will peel back that wallpaper. We will look at how telescopes actually observe the sky, at the trade-offs between depth and area, and at the hard limits set by time and technology. We will see how the brightest and nearest objects dominate our catalogues, while faint galaxies vanish into noise, and we will discover that the universe we talk about with confidence rests on an almost comically small sample of what really exists. Once you see how thin our slice of observation truly is, the night sky changes. It stops looking like a finished picture and starts to feel like the first few brushstrokes on a canvas that stretches far beyond what we can see. In everyday conversation, we throw around the word observed as if it had a single clear meaning. We say we have observed a galaxy, or we have observed the universe. It sounds simple. Something is there, we have seen it, story complete. In reality, there are layers hidden inside that word. First, you can notice that something exists at all. Then you can measure it well enough to log it in a catalogue. Only much later do you collect the detailed light that lets you know what that object really is. The gap between those layers is where the invisible universe hides. Start with the basic census. Over the past few decades, wide surveys have swept across the sky, taking relatively shallow images, just deep enough to pick up fuzzy smudges that stand out from the background. From those images, astronomers have catalogued somewhere between 10 million and 50 million galaxies. To keep the numbers simple, imagine we take the generous end of that range and call it 50 million. Set that next to the best estimate of about 2 trillion galaxies in the part of the universe we could in principle see. Suddenly 50 million begins to look very small. If there are 2 trillion galaxies out there, and we have catalogued 50 million, then the share we have even noticed is tiny. It works out to around 0.0025% of the total. Another way to picture it is this. For every one galaxy that appears as an entry in our databases, there are roughly 40,000 more that exist in the observable universe but have never been logged. Imagine trying to understand the history of all the cities on Earth when you have detailed information for only 25 of them, plus a vague awareness that the rest are out there somewhere. That is similar to what we are doing with galaxies. The famous Hubble Ultra Deep Field drives this home in a more visual way. Hubble was pointed at what looked like a nearly empty patch of sky and allowed to stare for hundreds of hours. Out of that apparent nothingness emerged about 10,000 galaxies, piled on top of one another in depth, some so faint that they were little more than whispers above the noise. Yet the area on the sky covered by that image is unbelievably small. It is roughly 1 part in many millions of the full celestial sphere. If the whole sky were shrunk down to the size of a continent, the ultra-deep field would be more like a small coin lying on the ground. That deep image is one of the most detailed windows we have into the distant universe, but it's still only a single keyhole. We have not taken similar exposures in most directions. Instead, the sky is a patchwork of shallow scans and narrow deep wells. So when we speak with confidence about how galaxies were distributed across the young universe, we are leaning heavily on what we learned from a few such wells, plus the assumptions of our models. Statistically, that can work very well, but it is not the same as having a complete map. Even within the set of galaxies that do appear in catalogues, there is a huge divide between a simple detection and a true study. A catalogue entry might tell you the rough position of the galaxy on the sky and how bright it appears. From this you can guess at its type and get a crude sense of its distance, but many different combinations of size, distance and age can produce similar looking smudges. To break that ambiguity, you need something more powerful than an image. You need a spectrum. A spectrum is what you get when you spread a galaxy's light out into its component wavelengths and measure how much light arrives at each colour. In those patterns are fingerprints of the elements in its stars and gas, the speed at which it is moving away from us, and therefore its distance, as well as clues about its age and star formation history. Spectroscopy is slower and more demanding than simple imaging. You often have to dedicate a whole observation to a small set of targets, guiding slits or fibres onto their positions, and you need long exposures to collect enough light for a clean result. Because of that cost, only a small fraction of catalogued galaxies have high-quality spectra. One of the great projects in this field has been the Sloan Digital Sky Survey, which ran for years and produced some of the most comprehensive maps of galaxies ever made. Sloan obtained spectra for on the order of a few million galaxies. That sounds like an incredible achievement, and it is, until you remember that we think there are about 2 trillion galaxies in the observable universe. 2 million out of 2 trillion is like trying to understand every city on Earth after actually walking the streets of a single neighbourhood. The difference between imaging and spectroscopy is like the difference between seeing a skyline from far away and actually visiting the city. From a distance you can tell that a city is there, you can measure how bright it looks, and maybe you can distinguish whether it is dominated by a few tall towers or a broad sprawl of low buildings. But you do not know what language people speak, what the culture is, or what industries drive the economy. For that, you have to walk the streets, listen, and gather detail. When we look at the universe, our catalogues of tens of millions of galaxies are mostly skylines. Our few million spectra are our scattered, incomplete city visits. This layered reality is the quiet secret behind almost every clean, simple number you hear about the cosmos. When we say that star formation peaked at a certain time in cosmic history, or that a certain kind of galaxy was more common in the past, those statements are built on the small subset of galaxies for which we have detailed information. We then use mathematics and simulations to infer how the unobserved majority behaves. Most of the time, this approach works astonishingly well, and new data match the predictions. But it is still an extrapolation, not a direct count. Once you see this structure, the phrase we have observed the universe starts to feel different. Yes, our telescopes have detected immense numbers of objects. Yes, our catalogues are full of entries with carefully measured positions and brightness. Yes, our spectra have opened rich windows into the physics of galaxies near and far. Yet compared to the 2 trillion galaxies that fill the part of space we could in principle see, our detailed studies are a tiny sample. The universe we talk about confidently is a model constructed from that sample, not the whole thing itself. In the next part, we will look more closely at how telescopes carve this sample out of the sky, and why they cannot simply survey everything, no matter how powerful they become. When you first see a giant telescope, it is easy to imagine it working like a radar sweeping a lighthouse beam across the sky. In that picture, you could just let it spin for long enough, and eventually you would have scanned everything. The truth is far less simple. Telescopes are more like very powerful but very narrow eyes. They can see incredibly faint things, or they can cover large areas, but not both at once. Every observation is a trade between time, depth, and area. The universe we know is carved out of those trade-offs. One of the most important limits is field of view, which is the patch of sky a telescope can see in a single exposure. You can feel this with your own eyes. When you stare straight ahead, you see a reasonably wide scene. Now imagine looking through a pair of binoculars. You can zoom in on distant details, but you lose the surroundings. Telescopes behave the same way. Instruments like the Hubble Space Telescope were designed for sharp detail, not wide coverage. A typical Hubble image covers an area of sky so small that you could hide it behind a grain of sand held at arm's length. James Webb goes even deeper in infrared light, but its field of view is also small. When Webb takes a deep image of a galaxy cluster, it reveals hundreds of background galaxies that no previous telescope could see. Yet that glorious image still samples only a tiny patch of the sky. To create a wide map, astronomers have to tilt and point the telescope again and again, stitching a mosaic afterward. Each tile costs precious observing time. Large ground-based survey telescopes work the other way around. They use cameras with enormous fields of view to sweep large fractions of the sky, but each single exposure is shallower and misses the faintest objects. The second major limit is exposure time. Light arrives at a telescope like raindrops into a bucket. Bright nearby objects pour in photons quickly, so you can capture a clean image in a short time. Faint distant galaxies send only a thin drizzle of light. To see them clearly, you have to keep the shutter open for a long time, so that enough photons accumulate above the random noise of the detector and the glow of the sky. The famous deep fields from Hubble are not a single photograph. They are stacks of many separate exposures added together over dozens or even hundreds of hours. Those long exposures come with a price. A single night on a large telescope might contain only a handful of such deep pointings, if that. Every additional minute you stare at one region of sky is a minute you cannot spend elsewhere. Wide surveys flip the balance. They take shorter exposures, just long enough to catch the brighter galaxies and stars and then move on. The result is a much larger map with many more objects, but it is biased toward the brightest and most easily detected sources. Invisible to the casual viewer is the choice hidden in the data. Do you want to know a little about many things or a lot about a few? Then there is the question of wavelength. Different kinds of light reveal different layers of the universe. Optical light, the kind our eyes see, shows stars and some types of gas. Infrared light reveals dust-shrouded regions and the red-shifted glow of very distant galaxies whose light has been stretched by cosmic expansion. Ultraviolet traces hot young stars. X-rays and gamma rays show violent events near black holes and exploding stars. No single telescope can cover all these bands with equal sensitivity. Each observatory is tuned to certain ranges, and each range demands different detectors, mirrors, and cooling systems. Space-based telescopes like Hubble and James Webb avoid atmospheric blurring and the blocking of many wavelengths by air. That gives them an enormous advantage in clarity and access to infrared and ultraviolet light. But they are also harder to build, repair, and upgrade. Their instruments are fixed once they are launched, their lifetimes are limited by fuel and hardware, and their observing schedules are packed years in advance. Ground-based observatories can be modified and expanded over time, but they must fight weather, turbulence, and the brightening of the night sky from human activity. All of these factors shape what parts of the universe we can study well and which parts remain in shadow. To actually create a map, astronomers design surveys. A survey is a plan that says which patches of sky to observe, for how long, and in which wavelengths. Some surveys focus on the celestial poles, where the geometry of the sky makes repeated coverage easier. Others avoid the bright band of the Milky Way to reduce confusion and dust. Some target regions where many other telescopes have already looked, so that new data can be combined with old. In practice, this means the sky is not evenly explored. There are deep, overlapping footprints in some directions and wide but shallow scans in others. Large areas remain relatively untouched. Even after the imaging is done, the really detailed work has barely begun. A photograph, no matter how deep, only tells you so much. To learn the distance to a galaxy, its speed, and its internal physics, you need spectroscopy. That means sending its light through a prism or a grating to spread it into a rainbow and measuring the intensity at each colour. Modern instruments can take spectra for many galaxies at once using fibres or slit masks, but there are strict limits. A single observation might capture a few hundred or a few thousand objects. Meanwhile, a deep image of the same field might contain tens or hundreds of thousands of faint galaxies. This mismatch turns spectroscopy into a bottleneck. There is no way to collect detailed spectra for every galaxy we can see in images, at least not with current technology and available telescope time. So astronomers must choose. They might select galaxies brighter than a certain limit, or lying in a certain range of colours that marks them as interesting. They might pick objects in a narrow stripe across the sky to trace large-scale structure. The result is a carefully designed but incomplete sample, a kind of scientific survey of only some of the residents in a vast city. Behind all of this is a very human constraint. Telescope time is fiercely limited. Major observatories invite proposals once or twice a year. Teams of scientists from all over the world submit detailed plans arguing why their project should be carried out. Committees review these requests and allocate time. Oversubscription rates are high. For some telescopes, researchers ask for 10 times more hours than are available. That means 9 out of 10 ideas, sometimes more, are turned away or delayed. The universe we see in our data is shaped not only by physics, but by these human decisions and priorities. When you hear that we have mapped the large-scale structure of the universe, or that we know how common different types of galaxies are, it is worth remembering how those maps are built. A telescope with a narrow field of view stares at a carefully chosen region for a carefully chosen time, in a carefully chosen wavelength. Another instrument takes spectra for a subset of the objects in that region. Proposals and schedules decide which patches of sky receive this attention, and which are left for another day that may never come. The picture of the cosmos that emerges from all this work is powerful and beautiful, but it is also partial. In the next part, we will step back in time and see how our map of the universe expanded from a single galaxy to an estimated 2 trillion, and why each leap forward also revealed how much we were still missing. A little more than a century ago, people thought the universe was basically the Milky Way. The bright band of stars across the night sky was taken as the main stage of everything that mattered. Beyond it, there might be some mysterious clouds, but nothing fundamentally different. Astronomers had drawn maps of star clusters and nebulae inside our galaxy, and felt they were closing in on the full layout of creation. The idea that our Milky Way could be only one island in a much larger ocean of galaxies was still controversial, and to many minds, unnecessary. Those mysterious spiral patches in the sky were the real troublemakers. Through early telescopes, they looked like small cloudy whirlpools, with arms wrapped around a bright centre. Some astronomers argue that these spirals were nearby gas clouds forming stars inside the Milky Way. Others suspected they were incredibly distant star systems in their own right, separate universes far outside our own. They called them island universes, a phrase that sounds poetic but was also deeply unsettling. If each spiral was its own vast system, then the Milky Way was not special at all. It was just one island among many. The debate came to a head in the early 20th century in what is now known as the Great Debate between two astronomers, Harlow Shapley and Heber Curtis. Shapley believed the Milky Way was enormous and that the spiral nebulae were inside it. Curtis argued that the Milky Way was more modest in size and that the spirals were separate star systems far beyond its edges. Both men looked at the same fuzzy photographs and the same patchy data. Each saw a different universe. At that point, the sky was still a puzzle without clear scale markings. The breakthrough came when telescopes and photographic plates became good enough to resolve individual stars in some of those spirals. Edwin Hubble focused on the Andromeda Nebula and similar objects and searched for a special kind of star called a Cepheid variable. Cepheids brighten and dim in a regular pattern, and the period of that pattern is tied to their true brightness. By comparing their intrinsic brightness to how bright they appear, you can measure their distance. Hubble found Cepheids in Andromeda that were far too faint and far too distant to fit inside any reasonable size for the Milky Way. Those distances forced a radical conclusion. Andromeda was not a nearby gas cloud. It was a separate galaxy, millions of light-years away, containing billions of stars of its own. The same logic applied to many other spirals. Overnight, the universe grew from a single city into a continent full of cities. The Milky Way became one galaxy among many, and the word galaxy itself took on its modern meaning. Human beings had discovered that we were living inside one island in a vast archipelago scattered through space. Once the idea of many galaxies was accepted, the next question was obvious. How many are there? Early estimates, based on the reach of the best telescopes at the time, suggested maybe tens of millions. As instruments improved and photographic surveys covered more of the sky, that number rose into the hundreds of millions. Each new survey revealed more faint smudges at the limit of detection. It was like turning up the sensitivity on a microphone and hearing voices that had always been there but were too quiet to notice. The late 20th and early 21st centuries brought a new kind of mapping tool. Digital detectors replaced photographic plates, computers took over the counting, and large systematic surveys were designed to sweep the sky in a regular, repeatable way. One of the most influential was the Sloan Digital Sky Survey. It used a dedicated telescope and wide-field camera to map large stretches of the sky in multiple colours, then followed up with spectra for millions of galaxies. For the first time, astronomers had a three-dimensional map of galaxy positions over a volume large enough to reveal filaments, clusters, and voids on truly cosmic scales. Even those impressive maps did not come close to capturing everything. Deep fields from the Hubble Space Telescope showed that if you stare long enough at what seems to be an empty patch of sky, thousands of faint galaxies appear, many at extreme distances. When researchers combined deep images with models of galaxy formation and cosmic structure, they realized that the early accounts were still missing a large population of small and faint systems. Many galaxies are simply too dim or too spread out in surface brightness to show up in shallower surveys. They hide below the detection threshold like distant ships below the horizon. By taking the observed galaxy counts in deep fields and correcting for the ones that lie just below detection, astronomers estimated that the total number of galaxies in the observable universe is on the order of 2 trillion. That number does not come from a direct census of every galaxy. It comes from combining deep pencil beam views with wide, shallower maps and with simulations of how structure grows under gravity. In other words, we dug a number of narrow wells through the sky, measured what we found, and then used physics to fill in the gaps between them. The shift from one galaxy to 2 trillion is one of the most dramatic expansions of scale in the history of science. It changes not only the numbers, but the way you feel about our place in the cosmos. At the start of the 20th century, humanity lived in a universe whose main feature was the Milky Way. Now we know that our galaxy is just one of trillions of systems, many of them larger, brighter, or stranger than our own. And yet, even with that enormous conceptual leap, we must admit that we have studied only a tiny fraction of those galaxies in real detail. There is a pattern hiding inside this story. Each time our instruments improve and our surveys go deeper or wider, the universe grows. New classes of galaxies appear, new structures emerge, and old estimates of total numbers climb. The value of 2 trillion is not a sacred constant. It is the current best estimate based on what we can see and what our models say should be there. Future telescopes may reveal that we have still been undercounting the smallest and faintest galaxies, especially in the early universe. The lesson is not that we were wrong, but that the universe is generous and keeps offering more than we first imagined. From the first arguments over spiral nebulae to the modern idea of trillions of galaxies, our map of the universe has expanded by orders of magnitude. Yet with every expansion we have also uncovered new blind spots. The early astronomers could not see that other galaxies existed at all. We can see that they exist, but we cannot yet study most of them closely. In the next part, we'll look at why so many galaxies remain too faint, too diffuse, or too redshifted for our current instruments, and how that simple fact quietly hides most of the universe from view. When you look at a crisp galaxy photo online, it is easy to forget how fragile that image is. Behind each beautiful spiral or glowing blob lies a fight against darkness and noise. Most galaxies are not bold, bright beacons screaming across the void. They're quiet whispers in a very noisy room. The laws of physics do not care that we are curious. They simply spread light out until almost everything becomes too faint for our instruments to notice. The first problem is simple distance. Light travels outward from a galaxy in every direction. As it spreads, it covers a larger and larger sphere. The farther away you are, the larger that sphere has become, and the thinner the light is stretched across it. That means the brightness of a galaxy drops rapidly as you move away from it. A galaxy that looks comfortably bright at 1 billion light-years can look 10 times fainter at a little over 3 billion light-years. By the time you push to the edge of the observable universe, many galaxies that are perfectly real fall below the threshold where a camera can reliably pick them out from the background. But distance alone is not the whole story. How that light is spread across the sky also matters. This is where surface brightness comes in. Imagine 2 galaxies that give us the same total amount of light. One is compact, with its stars crowded into a small patch. The other is puffed up and spread out. The compact one concentrates its light into a tiny area and stands out clearly against the darkness. The diffuse one smears the same light over a larger patch of sky. Each little patch looks only slightly brighter than the background glow. Even if the total light is the same, the spread-out galaxy is much harder to detect. Low-surface brightness galaxies are the ghosts of the cosmic population. Some are as large as the Milky Way, but so diffuse that their stars are scattered like a thin mist. Others are smaller dwarfs with only a few million stars drifting in a loose cloud. In an image, they can be nearly indistinguishable from subtle patterns in the noise. For a long time, our surveys were simply blind to them. Telescopes and cameras were tuned to pick up bright central regions and high-contrast features. Anything that faded gently into the background was likely to be ignored or misclassified as an artifact. The universe adds another layer of difficulty through its own expansion. As space stretches, the light from distant galaxies is stretched with it. Shorter wavelength light like blue and ultraviolet is shifted into red and then into infrared. The farther away a galaxy is, the more its light is shifted. This redshift dimming is a double blow. Photons are spread out over a wider range of wavelengths, and a portion of them slide into colours that older optical telescopes are not designed to detect. To see the most distant galaxies, you need infrared-sensitive instruments, very cold detectors, and long exposures. Before those tools existed, entire populations of early galaxies were simply invisible to us. Then there is the sky itself. From the ground, telescopes must look through a turbulent, glowing atmosphere. Air molecules scatter light. Water vapour and other gases emit their own faint glow. Human cities add their own haze of artificial light that scatters up into the sky and spills across observatory domes. Even at the darkest sites on Earth, the night sky is not perfectly black. It has a brightness of its own. Any galaxy whose surface brightness is too close to that sky level will be nearly impossible to detect. It is like trying to spot a faint pencil line drawn on paper that is already lightly shaded. Moonlight makes things worse. During bright phases of the moon, the sky background rises dramatically. Observers schedule their most sensitive deep imaging for moonless nights, and even then they must work around other constraints like weather and seasonal visibility. Clouds, dust and humidity all eat into the clarity of the sky. You can build the largest mirror in the world, but if the air above it is unstable or bright, your ability to see faint galaxies is sharply limited. Many of the most delicate observations are now done from space partly for this reason, but space telescopes cannot yet match the sheer collecting area of the biggest ground-based mirrors. Detector technology also sets hard boundaries. Early photographic plates were incredibly crude by modern standards. They wasted most of the photons that hit them. Modern digital sensors called charge-coupled devices are far more efficient, but they still have their own noise. Random variations in the electronics, cosmic rays striking the detector, and small imperfections in the pixels can all create little bright or dark spots. To reveal a faint galaxy, its light must rise above this noise in a consistent way. Otherwise, software may reject it as a glitch. That means many real but extremely faint objects, especially those spread out in low surface brightness, are filtered away. Even when the data are taken and stored, the story is not over. Huge surveys generate billions of detected sources. Algorithms are trained to decide what counts as a galaxy, what counts as a star, and what counts as junk. These algorithms are designed and tuned by humans, often using bright, clear examples. They do very well on the typical cases they were built for. They do less well on edge cases that look unusual, diffuse, or borderline. The faintest galaxies, the strangest shapes, and the most marginal detections are exactly the ones that are most likely to be misclassified or lost. Put all of this together and a pattern emerges. The galaxies that dominate our catalogues are not necessarily the most common galaxies in the universe. They are the ones that are easiest for our instruments and methods to find. Bright, compact systems with strong contrast against the sky are overrepresented. Faint dwarfs, diffuse giants, heavily dust-obscured systems, and very distant redshifted galaxies are underrepresented or missing entirely. Our mental picture of a typical galaxy is shaped by this selection effect. We imagine spirals with well-defined arms and bright centers, not because they are truly typical, but because they are the ones we can see best. This is not a failure of astronomy. It is a reminder that every observation is a negotiation with nature. Telescopes push back against distance, dimming, and noise, but those forces still win much of the time. The invisible universe is not empty. It is filled with objects that sit just below the line where our current tools lose their grip. As we build better instruments and smarter algorithms, some of those ghosts will come into view. Others will remain beyond reach, forever part of the dark backdrop we have to model rather than directly observe. In the next part, we will bring this down to a more familiar scale. If our surveys struggle to find faint galaxies across billions of light years, what about our own cosmic neighbourhood? It turns out that even around the Milky Way and our nearest neighbour Andromeda, tiny dim galaxies have been hiding in plain sight. They are the missing dwarfs in our own backyard, and they hint at just how incomplete our senses of the universe really is. If you wanted to find out how incomplete our picture of the universe really is, you would not need to travel to the edge of the observable cosmos. You could start right here, in our own neighbourhood. For most of the 20th century, astronomers thought they had a reasonably good handle on the galaxies near the Milky Way. There was our own system, the Andromeda Galaxy, a few bright companions like the Large and Small Magellanic Clouds, and a short list of other small neighbours. The local group felt like a familiar small town in an otherwise vast and distant universe. Then the data quietly changed the story. As digital surveys scanned the sky with sensitive detectors and clever software, astronomers began to notice odd little clumps of stars. These were not grand spirals or neat ellipticals. They were barely there, subtle overdensities of faint stars spread across a wide patch of sky. At first, some of them looked like they might be star clusters inside the Milky Way. But when researchers measured their motions and distances, a surprising pattern emerged. Many of these clumps were actually dwarf galaxies orbiting our own. Dwarf galaxies are the small cousins of systems like the Milky Way and Andromeda. Instead of hundreds of billions of stars, a dwarf might have a few million, or a few 100 million, or in the most extreme cases only a few thousand. Some are irregular clouds of stars and gas. Others are little spheroidal swarms with no clear structure. What they share is their fragility. They are easily disturbed by tidal forces from larger galaxies, and their light is easily lost against the foreground stars and dust of the Milky Way. In a crowded sky, they blend in almost perfectly. The tiniest of these systems are called ultra-faint dwarf galaxies. In terms of total light, some of them are dimmer than a single bright star. You would never see them as separate objects in a casual glance through a telescope. They are discovered statistically, By looking for patches of sky where the number and type of stars match what you would expect from a very small, ancient galaxy rather than from the Milky Way itself. It is like finding a hidden village not by seeing its houses directly, but by noticing that the local pattern of lights at night is just a little different from the surrounding countryside. What makes these dwarfs even more intriguing is that many of them seem to be dominated by dark matter. Dark matter is the invisible mass that does not emit light, but reveals itself through gravity. In a typical dwarf galaxy, the stars you can see account for only a small fraction of the total gravitational pull. The rest must be something unseen. That makes these galaxies valuable laboratories for studying dark matter. Yet for decades they were simply unknown, not because they were not there, but because our surveys were not sensitive enough and our methods were not tuned to recognize them. Simulations of cosmic structure had predicted something like this. When researchers model how dark matter clumps together under gravity, they find that a Milky Way-sized halo should contain hundreds of smaller subhalos, each a kind of miniature gravitational well. In the simplest picture, many of these subhalos should host small galaxies. But when astronomers counted up the known dwarf galaxies around the Milky Way, they found only a few dozen. This mismatch became known as the missing satellites problem. Either the simulations were wrong, or many of the predicted small galaxies were somehow invisible. As deeper surveys went online, the balance began to shift. Projects that mapped large areas of sky with higher sensitivity started to reveal new dwarfs, one after another. Many of them were discovered in data that had been sitting in archives for years, finally picked out by improved algorithms or revisited with new questions in mind. Every time an ultra-faint dwarf was confirmed, it suggested that there might be many more still hidden, especially in regions of the sky that are harder to observe, such as near the dense plane of the Milky Way. The story is similar around Andromeda. What once looked like a simple large spiral with a few known companions has turned out to be surrounded by a rich population of dwarfs, some arranged in curious planar structures. These satellite systems are not just decorations, they carry clues to the assembly history of their host galaxies. Some dwarfs appear to have been captured along with their own smaller groups, others show signs of being shredded by tidal forces, leaving streams of stars that wrap around the main galaxy like faint scars. All of this is happening on scales where our instruments are at their absolute best. The Milky Way and its surroundings are close by in cosmic terms, so individual stars can be resolved, and subtle structures can be teased out of the data. If we're still discovering new galaxies here, inside our own local group, then our ignorance must be far greater when we look out to distances where individual stars blur together and only the collective light of whole galaxies is visible. The missing satellites problem becomes less a crisis, and more a reminder that faint small galaxies can easily slip through our observational net. There is also a selection bias in how we have historically looked for galaxies. Surveys often avoid the dense band of the Milky Way, where dust and crowding make analysis harder. Yet that is exactly where some of the most interesting dwarfs might lurk, camouflaged behind layers of foreground stars. Specialized searches that focus specifically on these difficult regions have indeed turned up new objects. This suggests that our census is heavily shaped by convenience. We have explored the easy parts of the sky more thoroughly than the hard parts, and our picture of the local population reflects that. When you add all these pieces together, the local group starts to look less like a neat, finished diagram, and more like an evolving sketch. The Milky Way, Andromeda, and a handful of bright companions sit at the centre of our attention because they are obvious. Around them, a growing swarm of dwarfs is gradually coming into view, each one a reminder that the universe is more crowded and more structured than we assumed. Simulations still predict more small systems than we have found, but the gap is narrowing as observations improve and as models become more realistic about how hard it is for tiny galaxies to form and survive. The important lesson is not just about dwarf galaxies, it is about how incomplete even our local knowledge is. If we are still finding new galaxies in our own cosmic backyard, the idea that we have a comprehensive map of the wider universe becomes impossible to defend. The invisible universe is not only out there in the distant past, it is here, wrapped around our own galaxy, moving with us through space. In the next part, we will zoom back out again and look at how galaxies arrange themselves into vast structures, rings, arcs, and a cosmic web, much of which we have only recently begun to glimpse and much of which still lies beyond our direct view. If you could step outside the universe and look back, You would not see galaxies scattered at random like crumbs on a table. You would see structure. On the largest scales, matter in the universe forms a web of filaments and nodes, with huge clusters at the intersections and vast empty regions between them. It looks more like a network of veins in a leaf or foam in a bubble bath than a smooth mist. This is the cosmic web, and it is one of the most beautiful ideas in modern cosmology. It is also something we have only glimpsed in fragments. The basic outline of the web comes from gravity doing its slow work over billions of years. Tiny fluctuations in the early universe grew as denser regions pulled in more matter. Over time, these regions stretched into filaments and walls, with their intersections swelling into clusters and superclusters of galaxies. The spaces in between were drained, turning into enormous voids. Simulations that start from the conditions shortly after the Big Bang and let gravity run naturally produce this kind of pattern. When you look at their output, you see a universe filled with threads and knots. To see the cosmic web in reality, we need three-dimensional maps of where galaxies are in space, not just their positions on the sky. Projects like the Sloan Digital Sky Survey measured distances to millions of galaxies and revealed those maps for the first time. When astronomers plotted the data, they did not get a uniform sprinkling. They saw long chains of galaxies, giant walls, and sprawling clusters. They also saw huge gaps where very few galaxies live. These are the cosmic voids, regions that can span hundreds of millions of light years across. Voids are not completely empty. They contain some galaxies, but those galaxies are rare and lonely. Because they are isolated and often faint, they are harder to find than galaxies in crowded clusters. Many surveys have focused on dense regions because they are rich in targets. The web's emptier strands are less explored. That means our most detailed maps of the cosmic web are biased toward the bright knots and ridges. The quieter, more diffuse parts of the structure remain mostly inferred from models rather than directly traced. In recent years, attention has also turned to particularly striking features within this web. Astronomers have reported giant arcs and rings of galaxies that seem to line up over astonishing distances. One example is a structure nicknamed the Giant Arc, stretching across a large patch of sky and representing a chain of galaxies and clusters spanning billions of light years in length. Another is called the Big Ring, a loop of galaxies at similar distances that, when projected on the sky, forms an enormous circular pattern. These discoveries come from careful analysis of survey data, often by looking at the distribution of objects in specific slices of distance. These structures are fascinating, partly because of their sheer size and partly because they sit close to the limits of what our theories expect. Standard cosmology predicts that on very large scales, the universe should be statistically uniform. You can still get big filaments and walls, but truly enormous coherent features are rare. When something like the Giant Arc or the Big Ring shows up in the data, it sparks debate. Is this a real pattern in the universe, or a chance alignment pulled from noisy data? Are our surveys complete enough in that region to be sure? Different teams analyze the same catalogues and sometimes reach different conclusions about how unusual these structures really are. Whatever their final interpretation, these claimed giant features remind us of an important point. We are still in the stage of discovery when it comes to the larger scale patterns. Many of the most surprising structures were effectively invisible until survey depth, coverage, and analysis methods improved. Before the latest data, those galaxies were either not detected at all or not recognized as part of a coherent shape. The fact that such features can emerge from re-examining existing catalogues suggests there may be more waiting to be found as our tools sharpen. The cosmic web itself is also more than just galaxies. Much of its mass is in diffuse gas that fills filaments and feeds galaxies. This gas is called the warm, hot intergalactic medium. It is thin and hot, glowing mainly in faint ultraviolet and X-ray light that is extremely hard to detect. For a long time, this material was effectively invisible, leading to the so-called missing baryons problem, where a significant fraction of normal matter predicted by theory did not show up in observations. Only in recent years have telescopes begun to pick up hints of this gas, along filaments between clusters, confirming that much of the web is present in a form we can barely see. Gravitational lensing offers another way to trace the web. When light from distant galaxies passes near massive structures, its path is bent by gravity. By measuring subtle distortions in the shapes of background galaxies, astronomers can map the distribution of mass, including dark matter, in the foreground. These weak lensing maps reveal filaments that are not obvious in galaxy counts alone. Yet even here, the measurements are noisy and limited by the depth and resolution of the surveys. We see hints of the web's skeleton, not a crisp, detailed portrait. A key limitation in all of this is where we choose to look deeply. Many of the classic deep fields and detailed redshift surveys focus on specific regions of sky that were practical for long-term observation. They avoid the bright band of the Milky Way, where dust and stars cause confusion. They cluster near convenient declinations for certain observatories. This means our three-dimensional maps are dense in some directions and sparse in others. Imagine trying to understand the road network of an entire continent by mapping only a few major highways and ignoring everything that passes through mountains or forests. The broad outline might be right, but many important details are missing. There is also the issue of time. When we map the cosmic web, we're not seeing a frozen structure. We're seeing it at different stages of its life, depending on distance. Nearby filaments and clusters show the web in a relatively mature state. More distant regions show earlier stages, when filaments were thinner and clusters were less developed. We never see the entire web at one moment. Instead, our map mixes together snapshots from different cosmic eras. Reconstructing a single coherent picture from these staggered frames requires models, and those models lean heavily on simulations rather than direct observation. Taken together, all of this paints a humbling picture. We have solid evidence that the universe is threaded with a vast cosmic web, and we can trace parts of it with galaxies, gas, and gravitational lensing. We have intriguing hints of enormous arcs and rings that may push the limits of our theories. Yet the web we see is incomplete. Large regions are poorly mapped, faint filaments and lonely void galaxies are undercounted, and much of the mass in the web remains in forms that are only marginally detectable. The cosmic web is real, but most of its detail still belongs to the invisible universe. In the next part, we will turn from these grand patterns back to a very local obstacle. Even before we contend with faint filaments and distant clusters, our own galaxy stands in the way. Dust and stars in the Milky Way create a band across the sky that hides whatever lies behind it. This zone of avoidance literally blocks our view of part of the universe and reminds us that some of our blind spots begin right at home. If you look up on a clear night, the Milky Way looks like a gift, a rich river of stars crossing the darkness, full of structure and detail. For sky watchers, it is a source of wonder. For cosmologists, it is also a problem. That glowing band is made of stars and dust inside our own galaxy, and it lies directly in the way of whatever is behind it. When we try to map the universe beyond, the Milky Way does not politely step aside. It stretches across the sky like a thick curtain, hiding part of the cosmic stage from view. The main culprit is dust. Space is not just empty vacuum with stars sprinkled through it. The disk of the Milky Way contains clouds of gas mixed with tiny solid particles made of carbon and silicates. These dust grains are no bigger than smoke particles, but in large numbers they have a powerful effect on light. They absorb and scatter starlight, especially at shorter wavelengths like blue and ultraviolet. When light from a distant galaxy passes through these dusty regions, it is dimmed and reddened. If the dust is thick enough, the background galaxy can vanish completely in visible light. On a map of the sky, astronomers see this as a broad band where the density of stars and dust is high. They call the heavily obscured region the zone of avoidance. It is not that galaxies do not exist there, it is that we avoid looking in that direction when we use traditional optical surveys because the confusion is so great. Foreground stars crowd the field. Dust darkens the view. The background universe is still present, but its light is tangled up with the glow and shadows of our own galaxy. For a long time, this meant that large-scale maps of galaxy positions had a literal gap across the middle. Charts of the nearby universe showed sweeping structures and clusters above and below the plane of the Milky Way, and then a blank band where data was sparse. It was as if someone had taken a marker and drawn a thick line of censorship across the sky. Everyone knew that this was an observational artifact, not a real absence of galaxies. The question was how to see past the curtain. The key was to change the kind of light we use. Dust is very effective at blocking visible light, but it's much more transparent to longer wavelengths. Infrared light can slip through dusty regions that are opaque in the optical. Radio waves pass through even more easily, so astronomers began to hunt for hidden galaxies in the zone of avoidance using infrared and radio telescopes. Instead of looking for the starlight from those galaxies, They searched for the emission from their cool dust and their clouds of neutral hydrogen gas. These efforts paid off. In the 1990s, radio observations found a large galaxy now known as Dwingaloo 1 hiding behind the Milky Way in the constellation Cassiopeia. In visible light, it is so obscured by dust that it is almost undetectable. In radio wavelengths, its signal stands out clearly. Other surveys uncovered more galaxies and even whole clusters in the hidden band. Step by step, the blank region on our maps began to fill in, revealing structures that connect across the galactic plane. Some of the most intriguing discoveries relate to something called the Great Attractor, a region of mass that appears to tug on nearby galaxies, including the Milky Way, affecting their motions. Early studies showed that many galaxies seem to be drifting toward a common area of the sky, but that region lay behind the zone of avoidance. For years, astronomers had only rough clues about what was there. Infrared and radio surveys eventually revealed that the direction of the Great Attractor hosts rich clusters and superclusters partly hidden by the Milky Way, helping to explain the observed motions. The picture is still incomplete, but without peering through the dust, this entire part of the cosmic landscape would remain mysterious. Even with these tools, the obscured sky is not an easy place to work. Infrared detectors must cope with the glow of warm dust in our own galaxy. Radio telescopes have to separate the subtle signals from background hydrogen in distant galaxies from the stronger emission of gas inside the Milky Way. The density of foreground stars is so high near the galactic plane that automated algorithms often confuse faint background galaxies with blended stars. Careful modelling and cross-checking between different wavelengths are needed to be sure that a detected source is truly an external galaxy and not a quirk of local structure. When astronomers estimate how much of the sky is significantly affected by the zone of avoidance, they find that it is not a small sliver. Roughly 1/10 of the celestial sphere is heavily obscured, and a larger fraction is partially affected. That means we have a direct, relatively clear view of maybe 9/10 of the sky at optical wavelengths, and less than that if we're being cautious about subtle dust effects. The remaining part is a region where our maps are stitched together from more indirect data. We know there are galaxies there. We know there are filaments and clusters, yet our picture is more like a sketch than a detailed photograph. This matters for how we understand the large-scale structure of the universe. When we draw maps of nearby superclusters or voids, the shapes that cross the galactic plane are reconstructed from pieces. A structure might be obvious in the northern sky and again in the southern sky, with an uncertain middle section where the Milky Way blocks our view. In some cases, later infrared and radio surveys confirm that the two parts do connect through hidden galaxies. In others, the connection is weaker or more complex than first assumed. Our models of the cosmic web are strongest where we can see clearly, and most fragile where the zone of avoidance cuts across the data. There is also a subtle psychological effect. The Milky Way dominates the night sky visually, so our imagination naturally centers on it. When we look at a map of galaxies, the blank band where our own galaxy sits can reinforce the feeling that the Milky Way is somehow central or special. In reality, the band is simply a line of sight effect. If we could float far above the galactic disk and look back, we would see that our galaxy is just one of many, with no privileged place in the cosmic web. The zone of avoidance is less a cosmic feature and more a quirk of our vantage point inside a dusty disk. In the coming decades, new surveys will continue to chip away at this blind spot. Space-based infrared observatories and large radio arrays on Earth will map more of the hidden universe behind the Milky Way. Better models of dust distribution will help us correct optical data more accurately, but the core lesson will remain. Even on the sky we think we know, our own home galaxy hides a meaningful fraction of whatever lies beyond. The invisible universe begins right across the middle of our map. In the next part, we will leave our obstructed vantage point and use some of the brightest objects in the cosmos as our guides. Quasars and gravitational lenses act like lighthouses and magnifying glasses, letting us probe galaxies that would otherwise be far too faint to detect. They show us that even with clever tricks, we are sampling only a handful of narrow lines through an enormous unseen volume. When most galaxies are too faint and distant to see, you need shortcuts. You need cosmic cheats. Fortunately, the universe gives us a few. A tiny number of objects are so bright that they shine across most of cosmic history, and a tiny number of alignments bend space in our favour. These are our lighthouses and magnifying glasses. They let us peek far beyond what our telescopes could normally reach. They also reveal something unsettling. Even with these advantages, we're still sampling only a handful of narrow paths through a much larger unseen volume. The brightest beacons are quasars. A quasar is the blazing core of a galaxy whose central black hole is feeding aggressively. Gas spirals inward, heats to enormous temperatures, and radiates with the power of 1 trillion suns packed into a region smaller than our solar system. Seen from billions of light years away, the host galaxy can fade into the background, but the quasar itself is a sharp point of light. Some of the most distant known quasars come from a time when the universe was less than 1 billion years old. Quasars are useful for more than their spectacle. Their light does not travel through empty space. It threads its way through filaments of gas and clouds between galaxies. Each time that light passes through a patch of hydrogen, a small fraction is absorbed at specific wavelengths. By the time the quasar's light reaches us, its spectrum is etched with a forest of absorption lines, each one marking a different clump of material along the line of sight. By studying these patterns, astronomers can reconstruct the distribution and state of gas in the young universe, even when that gas is far too diffuse to see directly. That makes quasars like flashlights shining through fog. You do not see the fog itself very well, but you see its effect on the beam. From that, you can infer whether fog is thicker or thinner, cooler or hotter, more neutral or more ionized. In the early universe, this is especially important. There was a period when the first generations of stars and galaxies were just turning on, gradually ionizing the hydrogen that filled space. Quasar spectra carry the imprint of that transition. By measuring how their light is absorbed at different distances, we can trace when and how quickly the cosmic fog lifted. Even so, each quasar only probes one thin line through space. It is like drilling a single narrow well into the ground and trying to map an entire underground river system from that one core. To build a fuller picture, astronomers collect spectra from many quasars scattered across the sky. Yet the total number of known bright distant quasars is modest compared to the size of the universe. Our reconstruction of the early cosmic web from quasar sightlines is therefore powerful but statistical. We see patterns emerge when we combine many beams, but huge regions go unsampled. Our second major trick is gravitational lensing. According to general relativity, mass curves space. When light from a distant galaxy passes near a massive object such as a galaxy cluster, its path is bent. From our point of view, the background galaxy can appear stretched, magnified, or even multiplied into arcs and rings around the lensing mass. In effect, the cluster acts like a natural telescope, boosting the brightness of galaxies that would otherwise be too faint for us to detect. Some of the most distant and intrinsically faint galaxies known have been found this way, as distorted smudges behind massive clusters. Without lensing, their light would fall below our detection threshold. With lensing, their brightness jumps enough for our instruments to see them. By modelling the mass distribution in the lensing cluster, astronomers can reconstruct what the original background galaxy looks like and estimate how much it has been magnified. In this way, we glimpse star-forming systems from very early times that would normally be hidden. Strong lensing, where the effects are dramatic and obvious, is rare. It requires a nearly perfect alignment between a distant source, a massive lens, and us. Weak lensing, where the distortions are subtle, is more common, but it is harder to disentangle from noise and requires large samples of background galaxies. In both cases, we are at the mercy of chance alignments. We do not get to choose exactly which distant galaxies will be magnified for us. Nature picks a random subset and offers them up in distorted form. This randomness has an important consequence. The lensed galaxies we study in detail are not necessarily typical. They are biased towards certain environments and lines of sight. For example, they tend to lie behind particularly massive clusters, simply because those clusters make the strongest lenses. That means our most detailed views of very young small galaxies come from regions that happen to sit behind those rare heavyweights. The rest of the early universe remains far less accessible. Quasars have their own bias. They select galaxies whose central black holes are in an unusually active phase. Most galaxies, including our Milky Way, do not host such a blazing nucleus right now. The early universe may have had more active black holes on average, but even then, quasars represent a specific subset of galaxies, not the whole population. When we use them as probes of intergalactic gas, that is fine, because we care mostly about the material between galaxies. When we use them to understand galaxy evolution, we must remember that they are extremes. Together, Quasars and lenses give us an enhanced but still narrow view of the high redshift universe. A distant galaxy might first be noticed because its light is magnified by a foreground cluster. If that galaxy also contains an active nucleus, its quasar gives us a bright spectrum through which we can study the gas between us and it. For a moment, that one path through space becomes rich with information. Then we move a tiny angle on the sky, and the magic alignment is gone. The next line of sight may be far less revealing. With upcoming surveys, we will find many more quasars and many more lenses. Telescopes that scan large areas of sky repeatedly will catch transient brightening events, as stars and compact objects act as temporary lenses. Deeper imaging will reveal fainter arcs and stretched galaxies around clusters. New spectrographs will capture the light from a greater number of distant sources. Each addition will thicken our sampling of the invisible universe. Yet even in the best case, these methods will always be sparse. We are drawing a map of a continent by lighting up a few roads at night, not by seeing every tree. The message that emerges is familiar by now. The universe offers us a few powerful tools that let us see farther and fainter than our hardware alone would allow. Quasars light up the early fog. Gravitational lenses magnify the tiniest distant galaxies. Combined with our telescopes, they provide astonishing views of times and places we would otherwise never reach. At the same time, they underline how limited our perspective remains. For every lensed arc we can analyze and every quasar spectrum we can decode, there are countless others we will never see, marching on through an invisible cosmos. In the next part, we will shift focus from the very first galaxies to a later, more chaotic era often called cosmic noon, when star formation across the universe reached its peak. We will see how galaxies then were turbulent, merging, and rapidly changing, and how our observational limits make that busy middle chapter of cosmic history surprisingly hard to reconstruct. If you plot the rate at which the universe forms new stars over time, you do not get a flat line. You get a rise, a peak, and a long, slow decline. Billions of years ago, there was a period when galaxies were building stars at a furious pace compared to today. Astronomers sometimes call this period cosmic noon, the busy midday of galaxy growth. It sits roughly between 2 and 3 billion years after the Big Bang and stretches over a few billion years. In that era, the universe was not quiet and stately. It was restless, crowded, and loud. Galaxies at cosmic noon were often thick with cold gas, the raw fuel for star formation. Instead of smooth, well-behaved spiral arms, many showed clumpy knots where giant clouds collapsed and lit up with clusters of newborn stars. Their disks were turbulent, with gas swirling and colliding. Mergers between galaxies were more common than today, as gravity pulled systems together in the growing knots of the cosmic web. When two galaxies smashed through each other, gas could be driven inward, feeding both central black holes and intense starbursts that briefly turned the system into one of the brightest objects in the sky. We can get a hint of this in nearby examples. The antennae galaxies, for instance, are a pair of spirals in the middle of a collision. Long tidal tails arc out like thin arms, and the overlapping region between their cores is a maelstrom of star formation. The system is messy, chaotic, and dramatic. Scale that kind of activity up across a large fraction of galaxies in the universe, and you get a sense of what cosmic noon was like. The calm, thin disk of the Milky Way that you see today is more like a middle-aged galaxy. In its youth, it was likely much more unsettled. Our own future gives another clue. In several billion years, the Milky Way and Andromeda will collide and eventually merge into a single large galaxy. Simulations show that as they fall together, tidal forces will tear out long streams of stars and gas. Clouds of gas will be shocked and compressed, setting off new rounds of star formation. The central black holes will spiral together, possibly lighting up as an active nucleus along the way. For a time, our placid spiral halo will host fireworks that echo the typical conditions of cosmic noon. If this period was so important for building the galaxies we see now, you might expect that we would have an excellent observational record of it. In reality, this busy middle chapter of cosmic history is one of the hardest to see clearly. The galaxies of cosmic noon are far enough away that they look small and faint. Their star-forming regions are often heavily wrapped in dust, which absorbs ultraviolet and visible light and re-emits it in the infrared. Many of the most active systems are therefore almost invisible in the bands where our earlier surveys were strongest. When astronomers first measured the global history of star formation, they noticed an odd tension. Optical surveys that counted the light from young stars suggested one set of numbers. Radio and infrared observations that traced dust and gas suggested a much higher rate, especially around cosmic noon. The conclusion was that a significant portion of star formation was happening in dusty compact regions that were hidden from optical view. These dusty starburst galaxies were real, but they were undercounted in many surveys simply because they did not shine in the wavelengths that were easiest to observe. There is also a geometric issue. To study cosmic noon in detail, you need to collect enough light from galaxies at those distances to break it into spectra and to resolve their internal structures. That demands large telescopes, long exposures, and often space-based infrared instruments. We have done this for selected samples in carefully chosen deep fields, but we cannot yet perform that level of scrutiny for millions of galaxies spread across the whole sky. Once again, we face the trade-off between depth and breadth. We have several exquisitely detailed portraits and many more blurry outlines. Mergers add more complexity. When galaxies collide, their shapes become distorted and irregular. Their light can be dominated by short-lived bursts of star formation, and their central regions can flare with active black holes. It is harder to assign them simple labels like spiral or elliptical. It is also harder to model their evolution with simple recipes. In the nearby universe, we can study individual mergers in high resolution. At cosmic noon, we mostly see silhouettes and integrated spectra. Untangling the sequence of events inside those systems requires careful interpretation and simulations to fill in the unseen steps. Selection effects are particularly strong in this regime. Many of the key surveys that first charted the star formation history were limited to galaxies brighter than a certain threshold in the optical. That naturally favoured massive, relatively clean systems and missed low-mass, dusty, or extremely compact galaxies. Later surveys targeted infrared bright objects, which tilted the sample toward the most extreme starbursts. Both approaches taught us important things, but neither gave a complete picture. The true population at cosmic noon likely contains many galaxies that are modest in mass, moderately dusty, and just below the detection lines of earlier surveys. Even our best instruments face a limit set by surface brightness and angular size. A galaxy at cosmic noon might span tens of thousands of light years, but at its distance it appears as a small smudge only a few pixels across. Fine structures are blurred together, star-forming clumps merge into a single patch. Kinematic details about how gas and stars move inside the galaxy are difficult to extract. Newer instruments use tricks such as integral field spectroscopy to map motion and chemistry across these distant systems, but the number of galaxies that can be studied that way is still small compared to the vast population that exists. All of this means that the apparent neat story of galaxy evolution hides large uncertainties. We say that galaxies grew rapidly in the early universe, reached a peak in their star-forming activity around cosmic noon, and then gradually calmed down. That broad outline is well supported by data, yet the details of how individual galaxies moved along that path, how often they merged, how bursts of activity alternated with quiet phases, and how feedback from black holes and supernovae regulated their growth, are still topics of active research. Our direct observations give us a few key frames in the movie. The rest of the plot between those frames is reconstructed with the help of theory and simulation. The irony is that the era most responsible for shaping the galaxies we see today is also the era where our view is most patchy. The first galaxies are spectacular because they are new and rare, and we reach them with the help of lenses and deep infrared imaging. Nearby galaxies are easy to study in detail. The busy middle, where most of the building actually happened, is hard to observe across the full range of environments and masses. That middle is a major piece of the invisible universe, not because it lies beyond our horizon, but because dust, distance, and complexity conspire to blur it. In the next part, we will lean on one of our most powerful tools for bridging these gaps. Cosmological simulations allow us to grow virtual universes from simple starting conditions and see how galaxies should form, merge, and evolve. These simulated universes not only match many of the patterns we observe, they also highlight what must be missing from our direct surveys, and they reveal large parts of the cosmic population that are still effectively invisible to our telescopes. There is a moment in modern cosmology that feels almost like cheating. You take a box of virtual space, you sprinkle in tiny ripples that match what we see in the cosmic microwave background, you tell your computer the rules of gravity, gas physics, and radiation, and then you let it run. Slowly, filaments form, halos of dark matter grow, gas cools, falls in, and forms stars. After enough simulated time passes, you zoom out and the image on your screen looks uncannily like the real universe. Clusters, filaments, voids, and galaxies appear where before there was only a hazy early soup. These cosmological simulations are not just pretty visualizations, they are rigorous experiments. The initial conditions are set by measurements of the early universe. The underlying laws are the same equations of gravity, thermodynamics, and atomic physics that we test in other settings. Researchers tune the details of how stars form and how black holes feed and blow out gas, then compare the results with actual galaxy surveys. When a simulation matches many different observable properties at once, like the distribution of galaxy masses, the shapes of clusters, and the pattern of the cosmic web, it earns our trust as a kind of laboratory for the invisible. One of the striking results from these simulations is the sheer number of galaxies that naturally appear. When you simulate a volume equivalent to the observable universe, starting from early fluctuations of the size and strength that the cosmic microwave background reveals, you end up with on the order of 2 trillion distinct galaxy-sized systems by the present day. That number lines up well with the estimates we derive from deep surveys and statistical corrections. It is a reassuring sign that our broad picture of structure formation is on the right track, but simulations also make a more subtle point. They tell us not just how many galaxies there are, but what kinds of galaxies we ought to be missing. In the virtual universe, dark matter halos collapse across a wide range of sizes. Big halos host majestic spirals and giant ellipticals. Smaller halos host dwarfs and low-mass systems. Many of these small galaxies are faint and diffuse. Some form only a few stars before feedback and their shallow gravity halt further growth. Others sit in under dense regions, far from the bright nodes of the cosmic web. In the simulation, they are clearly there. In our telescopes, many of them vanish below detection limits. This helps explain puzzles like the missing satellites problem. As we saw earlier, early simulations predicted hundreds of dark matter subhalos around a galaxy like the Milky Way, while we had found only a few dozen dwarf companions. In the more modern, higher resolution runs, those subhalos are still there, but many of them never turn much gas into stars, or they form only a tiny ancient population. They would be extremely hard to spot in real data. The conclusion is not necessarily that the simulations are wrong, it is that our census is incomplete. The invisible population of ultra-faint dwarfs that simulations naturally produce is exactly what we would expect to be hidden from our view. Simulations also reveal how many galaxies should live in low-density regions, like the interiors of voids and the faint stretches of filaments between clusters. Observationally, these environments are challenging. Void galaxies are few and far between, so wide and deep surveys are needed to collect a decent sample. They are often small and faint, so they are easy to miss. In simulations, by contrast, it is straightforward to count them. The result is that our real sky catalogues seem to undersample these lonely systems. That undersampling matters, because such galaxies can carry unique information about how environment affects growth and star formation. Another powerful aspect of simulated universes is that they let us connect different snapshots in time. In the real universe, when we look farther away, we see earlier eras, but we never see any one galaxy age in real time. We catch it at a single cosmic moment. In a simulation, you can tag a galaxy at early times and follow its history as it merges, accretes gas and changes shape. You can see how often galaxies of a given mass today pass through starburst phases, how many mergers they experienced, and how their central black holes grew. That lets you test scenarios for galaxy evolution that would be impossible to watch directly. When you compare simulated populations at different times with what we actually observe at corresponding redshifts, you find a mostly encouraging match. The relationship between galaxy mass and star formation rate, the abundance of massive clusters, and the overall growth of structure all line up reasonably well, yet there are persistent mismatches at the faint end and in special environments. Simulations predict more small, low surface brightness galaxies than we have catalogued. They predict more stars in the outskirts of halos than some surveys show. They suggest that certain types of compact galaxies should be more common at intermediate times than we currently observe. At first glance, this might seem like a problem for the models, but the direction of the mismatch is important. Simulations often forecast more faint and diffuse objects than we see. Our instruments and methods are exactly most likely to miss faint and diffuse things. That points a finger at observational limits more strongly than at the underlying physics. It suggests that an invisible universe of small and subtle galaxies is entirely consistent with the data, and indeed expected, even if we have not yet directly tallied its members. There is another way simulations reveal our blind spots. In a virtual universe, you can easily measure statistics that are difficult or impossible to derive from real data. For example, you can ask what fraction of all stars ever formed live in galaxies fainter than a certain brightness, or what fraction of the total stellar mass resides in systems outside the reach of a given survey. Those answers depend on the details of the model, but they often show that a significant share of the cosmic story is happening in places we rarely see. A lot of star formation, especially at earlier times, may have occurred in galaxies that are now too small and faint for us to separate from the background. Simulations are not perfect. The physics of how stars form from cold gas, how supernova explosions stir and heat their surroundings, and how black holes launch jets and winds is complex. Much of it happens on scales too small to resolve directly in a huge cosmic run. Researchers use recipes that average over those small scales. Different choices can change the detailed outcome. That is why simulations are constantly being refined, compared with new observations, and updated when they fail important tests. Still, the broad convergence across many different groups gives confidence that the main message, especially about the abundance of small halos and faint galaxies, is robust. Perhaps the most important philosophical lesson from simulated universes is this. They show us a cosmos in which our observed slice looks perfectly normal, yet our observed slice is also obviously incomplete. The galaxies in our catalogues occupy the bright end of a much larger distribution. The structures in our maps trace the densest knots in a web that extends into regions we barely touch. When we lean on simulations to interpret data, we are not replacing reality with a cartoon. We are using the best available theory to fill in the parts of the picture that our instruments cannot yet paint. Absence of evidence is not evidence of absence. That phrase becomes very concrete when you compare the visible universe to its simulated counterpart. The fact that we have not directly imaged a certain type of faint galaxy in large numbers does not mean it is rare. It may simply mean that it lives below the floor of our current surveys. At the same time, if simulations predict vast populations of objects that leave no trace in any data set, then we must question the models. The dialogue goes both ways. Reality keeps our virtual universes honest. Virtual universes keep reminding us how much reality we are still missing. In the next part, we will turn directly to the messy business of data and statistics. Detection limits, noise, and selection biases shape every survey. We will see how astronomers try to correct for these effects and estimate the true cosmic census from an incomplete sample, and how those corrections push us back into the uncomfortable but truthful awareness that our map of the universe is built on extrapolation as much as on direct sight. If you wanted to design a machine that quietly lies to you, you could do worse than build a big survey telescope. Not because astronomers intend to deceive, but because every step in the chain from photon to catalogue bends reality a little. The sky is noisy. Detectors are imperfect. Algorithms must make yes or no choices. In the end, the universe that appears in our databases is not a neutral snapshot of what is out there. It is a filtered version, shaped by selection effects that prefer some objects and ignore others. Start at the rawest level, where photons hit the detector. A deep exposure is never just pure signal. The sky itself glows faintly. Random electronic noise adds tiny fluctuations in brightness from pixel to pixel. Cosmic rays slam into the detector and leave bright streaks or spots. Satellites and planes leave trails. Hot pixels misbehave. To pick out real galaxies from this mess, software must look for patterns that stand above the noise in a reliable way. It must decide how bright a patch has to be, how extended, and how consistent across exposures before it counts as something real. Those decisions are encoded in detection thresholds. If you set the bar too low, the catalogue fills with false positives, little clumps of noise masquerading as galaxies. If you set it too high, you miss real but faint objects. The safest choice for many surveys is to lean conservative. Better to miss the weakest sources than to publish a catalogue full of ghosts. That choice is understandable, but it means that just above the detection line you see only the brightest examples of a much larger hidden population. The floor beneath which we stop trusting the data is also the floor where the invisible universe begins. Even when a source is detected, its measured brightness is not perfect. Noise scatters some measurements upward and some downward, Imagine a population of galaxies clustered near the detection limit. A few will be nudged brighter by random fluctuations and pushed over the threshold. Others will be nudged fainter and vanish. Because there are usually more faint galaxies than bright ones, more objects are scattered up into the catalogue than down out of it. This bias makes the sample look slightly brighter on average than the true population. Subtle effects like this must be modelled and corrected if we want an honest census. Then there is the way surveys choose their targets. A flux-limited survey includes everything brighter than a certain apparent magnitude in a given band of light. That sounds neutral. In practice, it means that at greater distances you only see the most luminous galaxies. Nearby space is filled with big, small, bright and faint systems. Farther out, only the giants remain visible. If you build your picture of galaxy properties directly from such a sample, without correcting for this, you will conclude that galaxies in the distant universe are on average more luminous than those nearby, even if much of that difference is just selection. Astronomers can try to build volume-limited subsamples, where they include only galaxies that would still be visible if moved to the far edge of the survey volume. That helps, but it comes at a price. To keep the sample fair, you must throw away many of the fainter nearby galaxies that you did detect. You trade richness of detail for statistical cleanliness. Even then, the boundaries of the volume and the choices of bands and thresholds affect which types of galaxies are included. No sample is perfectly neutral. Everyone has a selection function, a kind of fingerprint that encodes the probability that an object with certain properties makes it into the catalogue. Colour cuts add another layer of bias. Many surveys use combinations of brightness in different filters to select interesting objects. Distant galaxies reddened by cosmic expansion, for example, can be picked out by their lack of light in bluer bands and their presence in redder ones. This method is powerful, but it is tuned to certain spectral shapes. Galaxies whose light does not follow the expected pattern, perhaps because of dust or unusual star formation histories, may be missed. Similarly, searches for quasars often rely on colour to separate them from ordinary stars. Any quasar whose colours fall outside the standard selection box is likely to be overlooked. Crowding and environment create their own issues. In dense regions like the cores of galaxy clusters, or in the band of the Milky Way, sources blend together. A faint galaxy near a bright star might be washed out entirely. Two galaxies that overlap on the sky might be mistaken for one. Automated pipelines do their best to deblend such cases, but errors slip through. As a result, catalogues are often more complete in sparse regions than in crowded ones. That can bias studies of how galaxy properties depend on environment, because the extremes of density are not sampled with equal fidelity. Spectroscopic follow-up, which we rely on for distances and detailed physics, is perhaps the most obviously selective stage. A deep image might contain hundreds of thousands of galaxies. A spectrograph with a finite number of fibers or slits can only observe a small fraction at once. Targets are chosen according to specific criteria. Maybe only galaxies brighter than some limit are selected. Maybe only objects within a certain range of colours or sizes. Maybe only a random subset in a stripe across the sky. The rest remain as photometric dots, their distances and detailed properties unknown. Once the spectra are measured, more cuts are made. Some spectra are too noisy to yield a reliable redshift. Some are contaminated by overlapping sources. Some show ambiguous features that software cannot classify automatically. These are dropped or sidelined. The end result, a clean catalogue of galaxies with solid distances and classifications, is a precious resource. It is also a filtered one, missing many edge cases and weak signals. When we use these samples to calibrate models or train machine learning algorithms, those models inherit the biases of the underlying data. Astronomers are acutely aware of these issues. Much of modern survey science is really the art of understanding and correcting for selection effects. Teams inject fake galaxies of known properties into images and see how many are recovered. They simulate noise and masking. They construct detailed maps of detection efficiency as a function of brightness, size, colour and position on the sky. These maps feed into statistical corrections that aim to reconstruct the true underlying distributions. When they say that a survey is 90% complete down to a certain brightness, that phrase rests on elaborate work behind the scenes. Even with such care, there are limits. Corrections can be made only within the space of properties that the survey touches at all. If a population of galaxies lives entirely below the detection threshold in all bands, or if it occupies a weird corner of parameter space never sampled in the first place, no amount of statistical gymnastics will conjure it into being. The invisible universe does not announce its presence. It leaves only indirect hints when models and observations disagree, or when simulations predict more variety than our catalogues reveal. This is where the uneasy partnership between data and theory becomes inevitable. To infer the full cosmic census, we must combine what we have actually seen with models of what we expect to be missing. We use simulations to estimate how many faint dwarfs or low surface brightness galaxies should exist below our limits. We use knowledge of detector performance to guess how many extended objects were lost in the noise. We fold in gravitational lensing, which measures mass even when it does not glow, to estimate how much dark matter lies in structures that host no obvious galaxies at all. The result is a picture of the universe that is both impressive and provisional. We have maps of millions of galaxies, measurements of large-scale structure, and a reasonably consistent story of cosmic history. Yet at every step that story is built on samples that are incomplete and biased, and on corrections that lean on assumptions and models. This does not make the story false, it makes it conditional. It reminds us that our confident statements about the universe are made with full awareness, that we see only a thin, filtered slice of what is really there. In the next part, we will push beyond observational limits into something even more final. There are regions of the universe that no telescope, no survey, and no future technology can ever reach, because the expansion of space itself keeps their light from us. The invisible universe is not only hidden by noise and bias. Parts of it are separated from us forever by the cosmic horizon, carving a hard edge into what we can, in principle, ever observe. So far, we have talked about the invisible universe as something we might someday uncover with better telescopes and smarter surveys. Faint dwarfs, dusty starbursts, hidden filaments. In principle, all of those could be brought into view if we had enough time, enough technology, and enough patience. Now we come to a harder boundary. There are regions of the universe that no instrument, no matter how advanced, will ever reveal. Not because they are faint, but because the fabric of space itself is carrying them away from us faster than their light can ever bridge the gap. To understand why, we need to separate two ideas that sound similar but are not the same. The observable universe is the region from which light has had time to reach us since the hot early stage we call the Big Bang. Because the universe has a finite age, there is a maximum distance from which any signal could have arrived by now. In all directions, that distance works out to a sphere around us with a radius of about 46.5 billion light-years. That is the part of the cosmos we could in principle see today if we had mapped every last photon. Yet there is a different horizon that matters just as much. It marks the boundary between regions whose light will eventually reach us and regions whose light, even if emitted right now, will never arrive. This is the cosmic event horizon. It exists because the universe is not just expanding, the expansion is accelerating, driven by something we call dark energy. On very large scales, space itself is stretching in such a way that the distance between us and very distant galaxies grows faster and faster over time. A common analogy is to imagine raisins baked into a rising loaf of bread. As the dough expands, every raisin sees all the others receding. The farther away another raisin is, the faster it seems to move away, because there is more dough stretching in between. In our universe, galaxies are like those raisins. They are mostly carried along by the expansion of space rather than flying through it under their own power. At some distance, the recession speed due to expansion exceeds the speed of light. That does not break the rules of relativity because nothing is moving through space faster than light. Instead, space itself is stretching. Light from a galaxy beyond a certain distance must fight that stretching to make progress toward us. In some cases, it can win. The light started out closer and has enough of a head start to reach us before the expansion pulls everything too far apart. In other cases, the space between us and the source grows so quickly that the light never closes the gap. It is like swimming toward a shore that recedes faster than you can swim. The water around you carries your strokes backward even as you try to push forward. No matter how long you keep going, the shoreline stays out of reach. This leads to a strange and slightly unsettling picture. Right now, we see millions of galaxies whose light has taken billions of years to arrive. Many of them are already beyond the distance at which new light, emitted today, could ever get here. We are seeing them as they were in the deep past, but we will never see their present or their far future. The signals that record those later chapters are stretched away from us by the accelerating expansion and will never cross the horizon. In that sense, our view of the universe is not just limited in space and time, it is permanently incomplete. Over the next tens of billions of years, this effect will grow stronger. More and more galaxies will cross the event horizon. Their light will be redshifted to longer and longer wavelengths, faded by expansion, until they slip below any reasonable detection limit, and then beyond the horizon entirely. For distant future astronomers, the night sky will look very different. The grand tapestry of clusters and filaments will thin out. Eventually, only the merged remnant of our local group, the combined descendant of the Milky Way, Andromeda, and their companions, will remain clearly visible. In that far future, someone studying the sky from within that single massive galaxy would see a universe that looks almost empty beyond their local halo. The cosmic microwave background would be stretched to such long wavelengths and such low energy that it would be effectively impossible to detect. The expansion itself would still be happening, but its evidence would have been erased from direct observation. Without deep theoretical clues, those observers might reasonably conclude that they lived in a static island universe surrounded by darkness, much like astronomers believed a century ago. This thought experiment drives home how privileged our current moment is. We live at a time when the universe is old enough that structures have fully formed, but young enough that many distant galaxies are still inside our observable sphere. The cosmic web is visible. The microwave background can be measured. The fingerprints of expansion and dark energy are written in the sky for us to read. In a sense, the universe is briefly transparent about its own history. That transparency will not last forever. It also sharpens the meaning of the phrase observable universe. Even if we somehow built perfect telescopes and mapped every galaxy whose light has reached us so far, we would still only be describing a bubble of reality centered on our position. Beyond that bubble, space continues, filled with more galaxies and structures, but causally disconnected from us. Their light will never touch our detectors. Their histories will never intersect ours. They are part of the universe in the full sense, but not part of the universe we can ever test. There is a kind of humility in accepting this. Human beings often like to imagine that with enough effort, every mystery can be solved, every hidden region can be explored. On Earth, that attitude works fairly well. You can always build a better ship or a faster aircraft and reach more distant lands. In cosmology, there is a hard limit built into the geometry of space and time. Past a certain point, the universe is not merely unknown. It is unknowable by any practical or even theoretical observation we could perform from here. That does not make the effort pointless. On the contrary, it makes the part we can explore more precious. Within our expanding horizon, light still carries messages from billions of years ago. Gravitational waves ripple past from distant mergers. Neutrinos stream through us from ancient nuclear furnaces. Every photon and particle that does arrive is a survivor from a universe that is constantly pushing things out of reach. The job of cosmology is to extract as much meaning as possible from those finite signals before time and expansion thin them out. It also reminds us that invisibility comes in layers. Some galaxies are hidden because they are faint or dusty or sitting behind the Milky Way. Others are hidden because they live in regions we have not yet surveyed, or in forms that our algorithms do not recognize. Beyond all of that lies a deeper invisibility set by the cosmic horizon, a boundary that mixing more telescope time or cleverer analysis cannot move. It is the ultimate edge between what we can know and what we must accept as forever beyond our sight. In the final part of this story, we will bring these ideas back to something very human. Knowing how small our observed slice of the universe really is changes how we think about life elsewhere, about certainty and science, and about our own place in the cosmos. The invisible universe is not just an astronomical curiosity, it is a lesson in humility, curiosity, and the open-endedness of exploration itself. By now the universe should already feel less like a finished picture and more like an unfinished sketch. We have talked about missing galaxies, hidden filaments, blind spots behind the Milky Way, and whole regions beyond our cosmic horizon. All of that is already humbling. Then we layer on one more question that has haunted people for decades. In all this vastness, with all these stars and planets, where is everyone else? On the face of it, the numbers look almost too generous. A typical galaxy like the Milky Way contains hundreds of billions of stars. Many of those stars have planets. A fraction of those planets sit in regions where liquid water could exist. Chemical reactions can build complex molecules in interstellar clouds and on young worlds. Given enough time, it feels almost inevitable that life would arise in more than one place. Not just bacteria and moss, but thinking, tool-using, signal-building life that could leave clues we might detect. That is the heart of what people often call the Fermi question. If even a small fraction of habitable worlds host intelligent civilizations, and if some of those civilizations have had millions of years to explore or communicate, why do we not see obvious signs of them in our sky? Why is there no glaring artificial signal, no bright engineered structure, no unmistakable footprint of technology on galactic scales? It is tempting to jump from that silence to a conclusion. Maybe we really are alone. The invisible universe pushes back hard on that temptation. Earlier we noted that only about 0.0025% of all galaxies in the observable universe have been studied in real detail. Inside the Milky Way itself, our best catalogues list on the order of a few billion stars, and only a small fraction of those have been examined closely for planets. That means that even in our own galaxy, we have not given serious attention to more than a thin skin of the stellar population. On cosmic scales, our search effort is closer to scratching at the surface of a single grain of sand. People sometimes imagine that we have been listening to the cosmos for a long time, sweeping vast volumes of space with sensitive ears. In reality, targeted searches for radio or laser signals from other civilizations cover tiny fractions of the possible parameter space. A radio telescope spends a certain number of hours pointing at a certain direction, scanning a certain range of frequencies. Most of the sky and most of the frequency bands go unobserved at any given time. Over decades, these searches add up, but compared to the number of stars and the range of ways a civilization might choose to communicate, they are still modest. There is also the question of timing. Our own planet has been around for more than 4 billion years. For almost all of that time, there were no radios, no cities, no clearly artificial signals at all. Human civilization has been leaking radio waves into space for only about a century. That is 100 years out of billions. If someone in another galaxy happened to look at Earth during most of its history, they would see a quiet world with no obvious signs of technology. Only in a very thin slice of time would they notice anything different, and even then they would need the right instruments and the right strategy to pick it up. The same logic applies in reverse. Suppose there are many civilizations scattered through the Milky Way or beyond. Each one might go through its own brief phase of radio loudness or other detectable activity. The odds that our listening just happens to overlap with their transmitting, in the right direction and at the right frequencies, are not obviously high. The cosmic haystack is not only large in space, it is also deep in time. Our search so far is more like glancing at one or two stalks and wondering why we have not found the needle. Another layer of uncertainty comes from our assumptions about what counts as a sign of life. Many searches focus on narrowband radio signals because such signals stand out cleanly from natural noise and are relatively easy for us to generate. That choice says more about our current technology than about any universal rule. A civilization that uses tight beams of communication directed at specific targets would not waste energy broadcasting in all directions. One that has advanced beyond heavy radio use might instead favour technologies we have not imagined or do not yet know how to detect. We are effectively looking under the streetlight, where it is easiest, not across the entire field. Exoplanet surveys add an important piece, but they come with their own selection effects. We have found thousands of planets by watching for tiny dips in starlight as they pass in front of their stars, or by measuring the wobble of stars as planets tug on them. These methods are biased toward large planets close to their stars and towards systems with favourable alignments to our line of sight. They tell us that planets are common, which is encouraging, but they do not yet provide a random, complete sample of Earth-like worlds at comfortable orbital distances. That means any estimate of habitable real estate is still heavily modelled rather than directly counted. When you overlay all of these limitations onto the Fermi question, the starkness softens. Instead of asking why a universe filled with life is not obvious, it becomes more honest to ask how confident we can be about any conclusion from such a small and biased sample. We have carefully examined the immediate neighbourhood of one ordinary star, taken a few deeper looks at a handful of others, pointed our ears in a limited way at a fraction of the sky, and looked for a narrow set of signal types. Then we compare that to a galaxy with hundreds of billions of stars and a universe with trillions of galaxies. In that context, the silence is not very informative. It does tell us that there are no glaring galaxy-spanning engineering projects in our immediate vicinity, nothing so spectacular that it would dominate our surveys. It suggests that loudly broadcasting civilizations are not common in the specific ways and places we have checked so far. Beyond that, the invisible universe leaves a lot of room. Civilizations could be rare but not absurdly rare. They could be common but short-lived. They could be quiet by choice or by constraint. They could be hidden behind the same observational limits that hide faint galaxies and diffuse gas. This does not mean that hope is enough. Science still demands evidence. It simply means that the absence of obvious signals so far does not strongly constrain the possibilities, given how small a fraction of space, time, and technology space we have actually explored. A more cautious and, in some ways, more exciting way to phrase the situation is this. We have barely begun to look. The fraction of the universe that has been surveyed for life with any seriousness is far smaller than the fraction that has been surveyed for galaxies, and we already know that our galaxy survey is missing most of what exists. Thinking about the invisible universe this way can change how the Fermi question feels. Instead of a verdict on a lonely cosmos, it becomes a reminder of how early we are in the search. The same humility we apply to galaxy counts and structure maps applies here. Our current non-detections are data points, but they sit on top of a mountain of unknowns. The right response is not despair or certainty, but curiosity and patience. The universe is large, our tools are young, and our sample so far is thin. In the final part, we will step back from the technical details and ask what this all means for us. Knowing that we see only a tiny biased slice of the cosmos can be unsettling. It can also be a source of wonder. The invisible universe is not a failure of our instruments. It is an invitation to keep exploring, to keep questioning, and to hold our conclusions lightly while we wait for the next wave of light to arrive. It is one thing to know, in an abstract way, that the universe is big. It is another thing to realize that almost everything we say about it rests on a thin slice of what we can actually see. We have spent this journey peeling back illusions about complete maps and well-measured skies. Along the way, the universe has turned from a finished picture into an unfinished conversation. Now the question becomes personal. What should it change in us, knowing that most of the cosmos is invisible, unknowable, or simply not yet explored? First, it should soften our certainty. Scientific stories are often presented as neat chains of facts, marching from cause to effect. It is easy to forget how much those chains rely on inference and statistics rather than direct counting. We measure a few million galaxies in detail and build models for 2 trillion. We observe a handful of distant quasars and reconstruct the state of gas across the early universe. This is not a flaw. It is how science must work when the thing being studied is so large that no direct census is possible. At the same time, this awareness is a kind of armor against overconfidence. When you hear bold statements about what the universe is really like, it helps to remember the smallness of our sample. We can say that certain models fit all the data we have, and that is powerful. We cannot honestly say that there is nothing left to surprise us. The invisible universe is a built-in reminder that every map is provisional, every equation is an approximation, and every tidy story sits on top of a noisy partial set of observations. Paradoxically, that uncertainty is part of what makes cosmology trustworthy. The best scientists do not hide the gaps, they quantify them. They publish error bars and completeness limits. They run simulations to see how many unseen galaxies might lurk below the detection floor. They argue, they revise, they change their minds when new data demand it. The invisible universe is not swept under the rug. It is acknowledged and wrestled with out in the open. That transparency is what turns ignorance from a weakness into a driving force. There is also a more playful side to all this. Knowing that most of the universe is still uncharted turns simple acts of observation into adventures. A new deep field from James Webb is not just another pretty picture. It is a core sample drilled into darkness, pulling up galaxies that have never been seen before. A clever algorithm that finds a few extra low-surface brightness dwarfs is not a minor tweak. It is proof that our tools can still surprise us, that the sky has not been exhausted. Each improvement in sensitivity or technique turns more of the invisible into the visible. On a human scale, the idea of living inside a barely sampled universe can be strangely comforting. We are used to hearing how small we are, how tiny Earth is against the backdrop of galaxies. That can feel crushing if you think size is the only measure that matters, But there is another way to see it. We are tiny, yes, but we're also one of the few species we know of that can look up, notice the darkness, and decide to do something about it. We build instruments that extend our senses across billions of light years. We turn a noisy drizzle of photons into stories about how everything came to be. The invisible universe also parallels something closer to home. Each of us lives with a small patch of experience and a massive unknown beyond it. We make models of other people, of societies, of futures, based on very limited information. We see only the bright moments of other lives, not the faint details in between. When you internalize how much of the cosmos is beyond your direct view, it becomes easier to admit that your picture of the world down here is also incomplete. That in turn can nudge you toward a little more humility, patience, and curiosity in everyday life. Looking ahead, the story is far from over. New telescopes will widen and deepen our surveys. Instruments on the ground will map weak gravitational lensing across huge swaths of sky, tracing dark matter more clearly. Space observatories will push infrared and X-ray sensitivity to levels we can only sketch right now. Each new facility will nibble away at the invisible universe, revealing more faint dwarfs, more diffuse filaments, more subtle signatures in the cosmic microwave background. None of them will make the universe fully transparent, but together they will turn the unknown from a blank wall into a rich landscape of questions. At the same time, we can expect surprises. When we extend our reach into new wavelengths or greater depths, we almost never find only what we expect. Pulsars, quasars, fast radio bursts, ultra-diffuse galaxies, giant arcs, these were not part of the earliest neat diagrams. They appeared because someone pointed a telescope in a new way, or looked harder at odd data points. The invisible universe is not just a dark reservoir of more of the same, it is a reservoir of things we do not have names for yet. That is not a reason to be afraid, it is a reason to keep looking. There is one more emotional twist. Thinking about the cosmic horizon, about regions forever beyond our reach, can feel like a loss. There are galaxies whose light will never reach us, histories that will never intersect ours. Yet there is also something beautiful in knowing that the universe is larger than our ability to grasp it. A universe in which we could in principle know everything might feel tidy, but it would also feel strangely small. An open, partly inaccessible universe leaves room for wonder. It leaves room for imagination to stretch into spaces that data will never fully fill. So what do you do with all of this the next time you step outside at night? You can still enjoy the familiar stars and the soft band of the Milky Way, but now you also carry a different picture. Behind every bright point in the sky, and in every dark patch between them, lie countless galaxies we will never see, and countless more we might see someday if we're clever enough. The visible universe is not a finished product. It is the thin, glowing edge of a much deeper reality. If that thought makes you feel small, let it also make you feel invited. Invited to keep asking questions, to support the instruments and missions that push our horizon outward, and to treat every new discovery not as the end of a story, but as the opening of another door. The universe is mostly invisible, yet from this small planet, in this brief moment, we get to light up a tiny part of it with understanding. That is an extraordinary privilege, and if you would like to keep walking further into that dark together, you know where to find us next.